All right, welcome back to machine learning. And I do want to apologize for having to do this online only again, but it is what it is. So here we are. Okay, so where are we? We are going to be talking about this MAP stuff, which is maximum posteriori estimation. We're going to finish this today, and then on Thursday, we're going to do a midterm review. And then the midterm is after the reading week. So the stuff on the midterm is going to be everything covered up to the end of today, and then on Thursday, it's just all midterm review. Okay, so yeah, let's get going with this map stuff. So last lecture, we ended with this maximum likelihood estimation. And maybe I go to the end of that to give you an idea where we ended off. So we had, okay, how did this happen? Oh, sorry. Yeah, the maximum likelihood business was over here. And our story with maximum likelihood was we said, okay, instead of using this like ERM learner and stuff that we've been doing before and estimating the expected loss, why don't we, well, we found that you can decompose this F-Bayes, which is like the best possible predictor. Okay, by decompose, I mean you plug in the squared loss and you assume that y is continuous, it's like r, and then you get this nice equation like this. And then you notice that, okay, if I just knew this conditional PDF here, then I'd be good in the sense that I can just explicitly calculate this integral. And that was kind of the idea of what MLE will give you. It will give you this PDF here, and then you can plug it in and get your predictor. And what we got at the end was that we plugged in also, Woching, I think you're unmuted. You might want to, yeah, okay, cool. So yeah, so the story was we had this F-Bayes thing, we wanted an estimate of it, so we got this like MLE estimate, and really what we did was we just estimated a parameter, this W MLE thing, which allowed us to have this PDF. And the way that kind of worked is we assumed that the PDF had some sort of distribution that was based on a parameter, like a normal distribution or something. And then once we had that, we had this like approximation part here, and then we just noticed, okay, we did some steps, and we found out that what we get back is really this linear equation, which was the exact same thing as we had from the ERM learner. And this is quite a coincidence. And yeah, a lot of people like this MLE stuff because they say it's more of like a principled or foundational way to think about this learning stuff. Like if you wanted to actually learn kind of the PDF of y given x, and you made this like normal distribution assumption, then you get back this thing here. And you didn't really have to assume what your loss function is or anything. You end up with something that is exactly actually the squared loss here that you need to minimize. Okay, so there's like this whole idea. And then I said, okay, so then there's another, like a whole other view of how you can learn this PDF P of y given x, and this is going to be this map stuff. And the idea is that like if your PDF P of y given x is based on a parameter, all you need to do is just going to be to learn that parameter. And there's different ways to do that. So let's go into this map stuff. Okay, in particular, this is kind of our goal. It's still going to be the same story as MLE. We really want to find an estimate of Bayes through this PDF here. And just the question is like, how are we going to learn this PDF? And yeah, and if you assume this PDF, just like in the MLE case, if we assume that this PDF is a function of some parameter W, okay, then to estimate this PDF, all you have to do is estimate that parameter. And MLE gave us a way to do that. Okay, so that's what MLE did. I'm just reviewing MLE one more time. It was said that like, how are we going to estimate this parameter? It said, well, let's look at this function called the likelihood function, which you can think of as kind of like the likelihood of the data for a given parameter. And this conditional thing was a little bit of an abusive notation because this wasn't actually a random variable here. It was really like you change the parameter, it changes this whole function. Okay, and so you're like, yeah, the way you thought about this was we want to find the W that maximizes the likelihood of the data. Okay, and what map is going to do, and this is a little, I'm just like kind of introducing in a slightly different way from how I told you, like how I introduced it last lecture, but we're going to get to that explanation in like 5 minutes. Okay, so what map is doing is instead of having this like P of D given W, which we were thinking as like the likelihood of the data, yeah, you want to find the W that maximizes the likelihood of the data. we're going to think of the map thing as the following, which is we want to maximize, or we want to find the W that is the most likely given the data. So, okay, so we've changed the order of these things, and this may seem a little bit like confusing and unclear why like you're doing this and what it really means. And maybe like the best way to kind of understand this, I think, is going to be to expand the definition of this term here, and then we can get some better understanding of it. But anyways, I say the English wording one more time, or how it's usually phrased, which is like map is trying to find the W that is the most likely given the data, while MLE was trying to find the W that maximizes the likelihood of the data. So things have been reversed. Okay, so what does this stuff actually really like mean, or how do we think about this term? So to do this, I'm going to expand the term, and we're going to find out some details. Okay. So what does this map thing do? It gives you a parameter. We're going to call it W map, right? Which is the solution to this argmax thing. So this is what W map is. Okay, and the one thing I want to mention just before I say this is there's some terminology that's used, and this thing here is often called the posterior. And we're going to see kind of why this word is used, and it makes sense in English, I guess, too. And this is where the map part comes from. It's like maximizing the posterior. Yeah, so I'll leave this word for now, and we'll come back to it in a second again. Okay, so we have this argmax business, and I want to expand this to have some more intuition as to what's going on. So what I'm going to do is I'm just going to use the definition of conditional probabilities, or conditional PDFs. And at this point, I also want to mention in map, we're actually going to think of W as being a random variable. So the W actually has some sort of distribution, and there's some probability and stuff of W being some value versus another. Okay, so how does this work? What is I erase this guy, and I just use the definition of conditional PDFs, which is it's the joint at the top divided by the marginal of the thing we're conditioning on, which is the data here. Oh. So this is the first step. Okay, so this is just definition of the PDF stuff. Second step is we're going to use the product rule for the numerator. And if you remember what the product rule says, it says that the joint distribution can be written as a conditional times a marginal. And we're going to do a different conditional than the one we started with. So in particular, we're going to choose this one, which is the probability of, or like the PDF of the data given the parameter times the marginal of the parameter W. Okay, and now one more step, which is here we're maximizing. Okay, well, maybe I point out this is product rule, and the other one was just a definition. Okay, so one more step is this is an argmax over the parameter W. And here the denominator has nothing to do with W. It doesn't depend on W. And we've seen this a couple times before, which is for maximizations or minimization problems, the constant doesn't change anything. This just scales what the function value is, or like adding a constant or subtracting one also doesn't change anything. Okay, so the maximum W is not affected by this term, so we can just remove it. Okay. And now we get to something that has some nice kind of interpretation as to what's going on. So what I do is I remove this denominator. And now we're left with this guy. Okay. Some things to note. So like, yeah, so we started with this, and now we go back to this. And first thing to note is, look at this guy. This is exactly the likelihood we've seen before, right? This is the likelihood of the data given some parameter. And now it's multiplied by the PDF of the parameter. This is like the marginal PDF of the parameter. And this term is called your prior. Okay, so now the interpretation of this map thing is that you're not trying to maximize the likelihood, but you're trying to maximize the likelihood scaled by some prior knowledge of what W's you're expecting to kind of have, like what the parameter should be. Okay, so one more time, if you just look at MLE, it's trying to find the W that maximizes this likelihood, while map is trying to find the W that maximizes the likelihood scaled by some what is called this prior knowledge of what W is. And so hence this is like kind of why we call this thing the posterior. This is like probability terminology, is that now this thing is what your probably like your what the PDF of W given D becomes after having some prior knowledge of, yeah. So you have some prior knowledge, you get some data, you update your prior knowledge in this way, and then you get like your posterior, which is like your new kind of understanding of the world and things like this. These are some terminology that gets used. Okay. So yeah, that's all I have to say about this. So now all that's really left after this intuition and understanding is we just need to solve this optimization problem again. And this is all going to be kind of just optimization stuff. And now we have this extra term to deal with, but it's going to be the same story where we apply like this logarithm and then take the negative of it and minimize, and things are going to look the same. But what we will find, of course, is that we're going to get a different solution than we got for MLE. So WMAP will not be WMLE. And it will be also a very interesting coincidence what it does end up equaling. Okay, so let us continue, if there's no questions, about actually doing this optimization and solving things. Okay. So before doing it for the actual case we care about, which is for this conditional PDF, I'm going to do it for some simpler setting, which is like we do some like basics of this map stuff when we have just one dimension, where the parameter is just one dimensional, so that we can get like an idea of how it looks. And then afterwards, we're going to come back to this conditional case, similar to what we did with MLE, and solve that case. And that'll be today. Okay. So let's do that. And to do that, I actually do a very similar problem to what we saw with MLE. So in MLE, we had this like Zi representing the some person's height, which turns out to actually, like people's height usually turns out to be normally distributed. And we said we like don't know what this true kind of mean parameter mu star is. So this is like the W that we were seeing above. This is our kind of unknown parameter. And we would like to estimate it somehow. And before we use MLE to estimate it, and now we're going to use map. Okay. And so in particular, since this is normally distributed, we have this data set that has NIID samples of Zi, same setup as before and everything. And this told us that basically the PDF of each one of these Zi's follows the following, which is like, it has this true mu star. Okay. And the extra assumption for this map stuff is now we need to make an assumption on the distribution, okay, of the parameter as well. In particular, if we want to maximize this, we need to make some assumption on what this PDF thing is. In MLE, we made an assumption on this guy. In map, we're going to make an assumption on this. Okay. So let's make that assumption. And in this case, this should be kind of like your prior knowledge. It should reflect kind of your prior knowledge of people's heights and things like this. So maybe one natural thing to assume is that the parameter is also normally distributed, and maybe the average height, you just assume, you take like a guess, that is going to be 160 centimeters for people. And the variance is just some value of sigma squared. I don't know. It doesn't, like, we're just gonna leave this as something we're not gonna really solve for. And we'll talk about like the interpretation of what this thing is after. Okay. So this is basically your prior knowledge. And in particular, since we assumed it's normal, its PDF has a very similar structure to above, which it has this 2 pi, but now there's this sigma squared down here. Okay. So yeah, as you can see, we kind of have like this guy now, and we have what we're going to use as the, well, we're going to use this for this term when we decompose it as a product in a second. So we're going to be able to solve this thing because we've made some assumptions. Okay, so let's solve and see how these things get plugged in. So we're interested in this mu map, okay, which is going to be an estimate. Once again, we're trying to estimate mu star here. Mu map is going to be an estimate of that. So how do we calculate that? We're going to calculate that by solving exactly this problem we had above. So I just copy and paste it. Okay. And now, of course, the parameter is not w, it's mu. So we're going to change w to mu. And for a normal distribution, the mean can be any number from negative infinity to infinity. So it belongs to the reals. And so here we have mu and mu. Okay. And so now the procedure is very similar to before. So you take this and you apply the logarithm function, and then you take its negative. The logarithm is because the product of things is going to become a lot simpler, and the negative is just because we like minimizing things. So you take the negative logarithm of this whole thing, and then you change the max to a minimum. Because we took the negative, we can do the minimum here. Okay. So I did kind of two steps at one. I took the log, which wouldn't affect the max, and then I took the min of the negative, which also is true, as we learned in optimization. Okay, but now what's nice is that this logarithm allows us to nicely expand the product of these two PDFs. So notice how these things are multiplied. This is the product of them. Well, you might remember there was, I guess I can write it quickly, it's like there was this property that we've used many times of the logarithm, and exactly kind of why we're using the logarithm here is that this holds. Okay. So that means we can take this and write it as a sum. So it's going to be the negative of this minus the log of this. Okay. So at this point, we have something that looks very similar to what we saw in MLE with an extra term, actually. So if you remember in MLE, we had exactly this term, and we were trying to just minimize this. So we had the argmin of just this, okay? And now what we have is this extra term over here that we also need to minimize jointly. And jointly, I mean like you have to minimize both of these things summed up. Okay. So the first thing is okay, so I'm not going to do all the steps that we did before, but you can simplify this after doing lots of steps that we did in the last class. And those steps are going to look something like write this as a product of all of the corresponding PDFs for each ZI. And you can do that because this data set, all the Zs were IID. So you can do this. And then you use the log to expand that product into sums and do some more, and then like simplify and so on and so on. And what you get to is what we had last class, and it was the following. So you can remove this, and after some simplification, what you will find is that this thing is equal to the sum from I equal 1 to n, and this became a sum due to the logarithm. And then we applied the logarithm to like the inside with the exponential and so on and so on. And what we found was that it looks like Zi minus mu squared over 2. Okay, so this was just from last class because this is the exact same term. So I just put that in. So what's left is to simplify this guy and then solve for the argmin. So what we do in blue is we're going to work with this second term for a while, get it to some simpler form, and then we plug it back in. And then we can solve this argmin. Okay. So we're going to work in particular with this term here. Okay. And I just want to point out one more time that at this point, we've done really nothing too special except for included this extra term compared to MLE. And including this, then we just kept it around, and that's why we have this extra term. So we just need to deal with that extra term. Okay, so how do we deal with it? Well, the first thing is like recall what the P of U thing is. We made an assumption about what this is, and because we made an assumption, we can just plug that directly in, which is we assumed it has a normal P, like its PDF is from the normal distribution. So let's just take that and plug that right in. Okay. So this would be the log of this guy. Oh. Good. Okay. And at this point, I guess you should already see that there's going to be some nice results from this. Like, first of all, there's two things multiplied together, which the log will allow us to write as a plus between these two things. Okay, so let's do that. Yeah. And I just do want to emphasize that this, like, you can do this for all sorts of different distributions, and this procedure is very like standard or similar. So it's good to, I guess, get familiar with these steps. Okay, so once again, just use the log property of the product of two things. Now, as you can see, the log of the exponential, that's just, they both cancel out. So we can remove that and get this simplified form. Okay, so remove that. This plus will become the negative here. We don't need these two brackets. And we get this. Okay, so this is hopefully much simpler. I mean, you can actually see the explicit dependence on mu here. Great. So we return back to minimizing this, and we plug this back in. So remove this. And we plug in what we just simplified for that log term. Okay. And we have to be careful because there is the negative here, and we only focused on this, so we need to make sure we expand the negative, or like, apply the negative through everything. So this would be negative, and then this will become a plus. Okay, so we're left with this minimization problem, and now we have like actually explicit dependence on mu everywhere, and there's no more like hidden terms and stuff like this. Okay, so now we just minimize. And to minimize, we make one more observation, which is that this term, which we've done before, this term has no dependence on mu. It's just a constant in terms of mu. And once again, if you shift your function by a constant, or minus or plus a constant, it doesn't change the minimizer. So we can remove this guy. So we take this, and we remove the middle term. And now we're left with an optimization problem that is not too different from what we had before, except we have just one new term here. Okay, and so now let's just solve this. And what that means is we have a function, g, it's a function of mu. And how do we solve for the argmin? Well, we take the derivative and set it to 0. And it turns out that this function is indeed convex, which you can take the second derivative and see that it's always positive to do this, and so on. So, but for now, I just tell you that. And so let's take the first derivative and set it to 0. So dg d mu of mu. Okay. So we've already done the first derivative of this guy from last class. And that just becomes, so the 2 comes out, right? And then you're left with this term, and then the 2 cancels out with this. So you have I equal 1 to n of just zi minus mu. Now we have this new term. We need to take its derivative. And so the derivative in terms of mu is just you take the 2, comes out to the front, and you're left with this, and this 2 and this 2 cancel. So we're left with mu minus 160 over sigma squared. Okay, and we want to find the mu that minimizes the above, so we need to set this derivative to 0. Cool. So now to solve this, we just need to rearrange and solve for mu. So let us do that. So to simplify some things, we first write out the sum as 2 separate terms. So it has this sum over zi, and then we have a sum over mu n times. But mu added up n times, the mu doesn't depend on I at all. It just becomes n times mu. And then we expand this term as well, the next term, and this becomes mu over sigma squared minus 160 over sigma squared. Okay, and we want this to equal 0. Now we can move terms from like left to right, and so, oh, there's one thing, which is this should be a minus. Okay. And now we just move things left to right and whatnot. So I'm going to move all the terms depending on mu to the right. And so what I get is the sum from I equal 1 to n of zi minus 160 sigma squared equals to n, I'm going to put this in brackets, minus 1 over sigma squared times mu. Okay, so that's just these two terms on the right. And now my goal was to solve for mu. So I can solve by mu by dividing both sides by this, and so I get the final solution, which is that mu, which is like this thing is really mu map. That was our goal. So that's equal to this mu thing we just solved for. And what that equals is this kind of complicated looking fraction, but it has a nice interpretation. Okay, so we get this fraction. And so this is, we've got our first ever like map solution. So we've solved for the parameter mu. That was our goal. What was it supposed to represent? It was supposed to represent the mean height of a person. So we got an estimate of it. What is our estimate? Well, it's this equation. What was it for MLE? Maybe I remind you. So for MLE, this estimate was not what we had here. It was something else. It was the sum I equal 1 to n of zi over n. So what it did not have is these terms, which are now based on our prior. Okay, but it's sort of related. Okay, and so then there's some special cases to understand what did this prior do. Okay, so like maybe let's build some intuition to look at these special cases. So the prior told us that we think, basically it says, okay, we had a prior in mu, which tells us like we had some past information for some reason that we thought mu was going to be some value. And here we thought that mu would have like, for some reason, and I guess it makes sense that the expected height of someone would be 160, and then it would have some variance of sigma squared. We can plug in anything, and we're going to see how the different values of sigma squared will affect this. Okay. But in some sense, what you're doing is you're kind of like, I guess in English, is you're biasing the mu, you're forcing the mu kind of to be somewhere around 160. Okay, so how do we see this mathematically? Well, we do some cases. First of all, if n is large, right? So if you have a lot of data, that's what n means, n being large is. Then what you'll find is that your prior information it just gets kind of removed. It's not very important anymore, in the sense that this becomes very, very large. So this is almost nothing. This is subtracting from almost nothing. And similarly, if n is really large here, you're summing a bunch of terms together, which this term becomes very large, and this almost becomes nothing as well. So what you find is that if n is large, then mu map is approximately equal to just the following, right? And this should make some sense. It kind of like washes out, people say like washes out your prior information. So all this extra prior stuff gets removed, and what you are left with is just the estimate based on basically your data. If you have a lot of data, then your prior knowledge is not very important anymore. And what you get back is that mu map is approximately equal to mu MLE. So these estimates are equal when you have a lot of data. So a very important kind of observation that happens with map. Second important observation is, is you can think about like, okay, how likely, or like, sorry, not how confident are you in your prior? And the way to think about this is like, okay, this thing has a mean of 160, or like its expected value is 160, but like your confidence can be expressed by how much variance you put on your prior. If there's zero variance, then you basically have 100% confidence. It has to be 160. Well, if the variance is very, very large, this would mean that your prior knowledge is like not very strong, and you wouldn't have much confidence that it's 160, in the sense that the distribution of this thing is very, very spread out, right? That's what high variance would mean. So we could look at these two cases, which is if sigma squared is small, so you're very confident in your prior, then what happens? If sigma squared is really small, right, then this thing is really small, which means that this is really, really large, and it dominates this term. Similarly, if sigma squared is really small here, this is really big, and it also dominates this term. What you're left with is then 160 over sigma squared, and then over this term here. So let's just write it. Then what you get is mu map is approximately equal to negative 160 over sigma squared over negative 1 over sigma squared. But you might notice this is exactly just equal to 160. And so what we get is that basically if there's very little variance in your prior, meaning you're very, very confident in your prior, what you find is that your estimate is just your prior. Almost no data, the data has almost no effect on what you expect it to be. And this should also make sense. Okay, so then obviously the other case, if sigma squared is large, then you have almost no confidence in your prior. And this is a very important case, actually, because we will see this in a second for the actual supervised learning stuff we're doing, which is that if you make sigma squared really, really large, you basically have no confidence in your prior. Like it has almost, okay, let me just draw one more. Okay, let's say this, and then I'll draw a plot. So if sigma squared is really large, then what happens is you find that mu map is approximately equal to mu MLE. Because if you look at it, this is very, okay, so if this is really, really large, this is almost 0. If this is really, really large, the variance, then this is almost 0, and you get back these two things. So it's almost mu MLE. And you can think of this, and this is really important, you can think of this variance here being really, really large as the same thing as if the PDF of mu is approximately a constant. Okay. So it means that for any value of mu, you kind of have the same amount of density. Okay. Yeah. It turns out this is not, okay, so I should say, yeah. So if this is the case, and I guess I should put approximately, because it turns, and I don't want to get into the details of all this, but like it turns out you can't have a uniform distribution over some random variable, which is this parameter here, that's over the real line. And there's some problem with this. But you can get something really, really close to a uniform distribution. So right, this is basically saying this is a uniform distribution. It's just some value always. It has no dependence on the parameter. It's always the same. And so you can get really, really close by making the variance very, very large. And the plot kind of is the following, if you might remember, which is for these normal distributions. What you'll find is like maybe this is like some normal variance one, I don't know, like, and then if you make the variance much smaller, or sorry, much larger, what you'll find is that the normal distribution looks as follows. It almost looks uniform. And so this is like large sigma squared. And so yeah, so if you make sigma squared really, really large, it almost looks like a uniform density. Sorry, these are the densities. And that would just look like a constant term. Okay. And so the important thing is that if the density is this constant, well, then this mu MLE, or sorry, map, is also equal to mu MLE. And the way to see this is, okay, you can see it as being through this case, but you could also see it if this is the case where it's almost a constant. When you go back to this optimization problem, you would have noticed right here that if you plug the constant in here, right, which is what this is just, it would just be C in here, you would find that it has no dependence on mu, and this would not affect the optimization problem at all. So what you get back is just the MLE problem. Okay, so these are some important observations, that when does map look like MLE and so on. And then really the important thing is, if your variance is small, meaning you're confident in your prior, what you get is that mu map is no longer mu MLE, and really your prior affects things. And in the extreme case, when it's really, really small, your prior is kind of all that the mu map is. It's your prior knowledge. Okay. Are there any questions about that? Because the next thing we do is go into applying this to the conditional PDF version for supervised learning and solve for the conditional PDF of y given x. Okay, wow. No questions today. Okay, let's continue then. So, yeah, all that's left is to solve for this PDF of y given x, which is like, why do we want to solve for this thing, or get an estimate of this thing? Well, it's because if we have it, then we solve for that integral and get f base, right? We get an estimate of f base. And then we have ourselves a predictor. Okay, so how do we do that? So the setting, like these first three parts are the same as what we saw for MLE. So you have some data. In this case, it's these feature label pairs. Okay. Each one of these feature label pairs are independent and identically distributed. This means that they have some distribution x, y, and they all have the same distribution, and they all have the same PDF or PMF, P of x, s, y. In this case, this is a joint PDF because it's the regression setting. Okay, and then the assumption we made in MLE, which is the one we're going to make now as well, is that the conditional distribution of the label y given the feature x is normally distributed with variance 1, but importantly that the mean, or the expected value, follows this linear relationship, which is there is some parameter w star that when you multiply it by the corresponding feature, you get the mean of this conditional distribution. So you can model relationships where, like, as x increases, right, if w star is just like some number, let's say in the 1D case, as x is increasing, then what you'll get is a larger mean, meaning your label increases. So like if the number of rooms of a house increases, you would find that the price also increases. And you can model these kind of linear relationships with respect to the features. Why it should be normal was we talked about that this is like just an assumption we make and is up for debate whether it's reasonable and whatnot. But it is the standard kind of assumption for this linear regression setting. Okay. Now what's left? Okay, so like, I guess this is actually still the same thing as before, which is this just implies that the PDF of y given x has the following thing, right? This is just the definition of the normal distributions PDF. Okay. The new thing is we need to make some assumption for map to work on the prior, what is like the prior distribution on our parameter w. Okay, so in particular, we're going to have to make some assumption on this. And this thing is a vector now, right? Before we had this, like in the previous example, we just had one parameter. Now we have a vector which has like d plus 1 indices in it. So what we're going to do is we're going to assume that each one of the indices of this vector has a certain type of distribution. Okay, and once again, this is just purely an assumption that gets made, and we're going to work with it, and you're going to find out what happens, and it turns out to be nice. And then we can talk about the assumption and its reasonableness and how reasonable it is afterwards. Okay, so the assumption is that each one of these parameters, their indices, are also normally distributed. And I don't know, for lack of knowledge, you have no idea like what the weights should be, these parameters. So you say that their mean should be 0, or maybe you like, okay, well, we'll talk about the interpretation of this, but like you would kind of like, maybe you'd want them to be 0, so you don't want it to be like too complicated of a predictor, if you remember this regularization stuff and whatever. But anyways, let's go with it. So you have these weights, you assume their mean is 0, but what you're gonna be interested in is picking what the variance should be. Okay, and you're gonna assume that the variance is this 1 over lambda squared business here. Okay, let me see one thing. Right, I don't think we need the squared here. Okay, let me just, we'll see if this is, I'm pretty sure you just need the 1 over lambda here. Okay, so we make this assumption. We'll find out in a second whether you need it squared, but each one of these wj's has this normal distribution with variance 1 over lambda. Okay, and lambda is just going to be some parameter similar to sigma squared above here, right? We had the sigma squared. It was just a parameter, like it was some other term, and we're going to talk about what value you choose, and it's based on your prior knowledge. So it's going to like how confident you are in that the weights should be 0 is going to change what this lambda is. Okay, so let's get back. So we're going to assume each one of these are also IID. So each one of the indices of the parameter of the weights is IID. Each one of these is IID. And this is for j equal to, for an element of not 0 to d, but it's just going to be 1 to d. Okay, so you're going to assume that the weights or the parameters for all indices from 1 to d have this normal distribution. And then remember that the 0th index was this bias term. And what's going to turn out to be the case is that you don't want to make any assumption on this. And yeah, so let's just do this and we'll talk again about the interpretation later. So what you're going to do is you're going to say, okay, you're going to need to make an assumption, but the way to make it basically like you have no prior knowledge is to use what we said before, which is you're going to assume it has whatever, 0 mean, but then you're going to say it has some variance sigma squared for a very large sigma. Okay. And this is basically going to make this prior not have any effect on the solution. Ideally, so in the case where things are discrete, you would just say that this is uniform. This is what you really want to say, that this is just the uniform distribution, so it's just a constant. And you'd want to say something like this, but you can do this for any finite a, but what you can't do is make it that it's uniform over the entire real line. And once again, I don't want to get into the details of this, but it turns out you cannot have a uniform distribution over the real line. So what you can think of this for very large sigma, you can think of it as having a uniform distribution for large a. Okay, so it's like a uniform distribution over almost all possible values, but it has to stop at some a, finite. Okay, and the point is to make it such that you have no prior knowledge of the bias term. Okay, so now let's solve this problem and then talk about the interpretation of the solution next, or after that. So to solve this problem, we just follow the same process as we did above and for MLE and so on. So you want to solve for W map, which is the parameter you want to solve for. It's a vector now, okay? And you want to minimize this. You want to find the W that makes this PDF the most, that makes this the largest given some data, right? This is what we've been doing. And then we do, after some steps that we saw earlier, what you can do is you can rearrange it in this way such that it looks like the likelihood times the prior. So far we've done nothing new. We've already seen this. So same exact steps. Now the next thing we do is also very similar to what we saw before, which is we apply the logarithm and then take the negative so that we can minimize. So we apply the log. There's going to be a negative out here, and then we're minimizing. So far should be very similar steps to what we've seen until now. And then we do one more thing, which is also looks very similar. Let me just put the brackets around this. Is that since it's the log of the product, we can expand the log into the sum. Great. So we've got to here. And now we're left with a problem that looks partly like similar to the MLE case. So in particular, this term is exactly the same term we saw in MLE for this exact problem, because we had the same assumptions on y conditioned on x being normal and so on. And so if we just plug in the definition, like this PDF definition into here, okay, well, we would expand this thing as like the product of these guys and do everything we did in MLE. It's all the same. And you plug in everything, what you will end up with is exactly what we had in the MLE thing. So I'm not going to redo all of that. I'm just going to plug in what we got in the MLE thing from simplifying. And what we got there was that this is equal to the sum of I equal 1 to n of yi minus the xi feature transpose w squared over 2. Okay, and also very similar to the previous example, where here this is just used to be mu, now it's this linear relationship for the mean, so it should make sense. Again, what's left is to talk about this term. This is the new term. It's part of it comes from the prior. Yeah, so we're gonna spend a little bit of time on doing this because now this guy is a vector, and it's gonna be a little bit more complicated than what we saw in the last example. But that's what we're gonna do next. And I'm gonna answer the question now, which was like, will we be able to essentially always plug in this MLE result when doing these type of problems? And the answer is yes. So for map, you're always going to get to this. And then you can always do this step, which means you can always do this step. So you can always get to there. So nothing will change there. And then you already, if you had the MLE result, you would just plug that in for look, like what I mean by MLE result is like if you already simplified this to solve your MLE problem, you would plug it in. What you do not plug in is you don't plug in the argmin of this, right? So what I'm plugging in is a simplification of like just the mathematical simplification of this term. What I'm not doing is I'm not finding the argmin of just this, right? I need to find the argmin of this thing jointly. So what I'm left with is to expand this term now. And once I have that, then I actually solve for the argument. So there's this mistake that one could make, which is to actually plug in the MLE solution. So I'm not plugging in the MLE solution. I'm just plugging in this simplification to this term from when we tried to find the MLE solution. And yes, exactly. The main difference in this map stuff is exactly in how we're handling the prior knowledge. So you can think of MLE. Let's go back here. It's actually important. You can think of MLE as map, like a specific case of map where your prior knowledge is just like you have no prior knowledge. And that would be represented by very high variance or having like a constant prior. If your prior is just everything is equally likely, then you just return back to MLE. However, map is like more general in the sense that if you did have some prior knowledge, you can use that and you will have a different solution. And yeah, that could reflect your prior. And like some of the time you will have some prior knowledge. For instance, with people's height, like you know people's height is not going to be negative 100 meters. So you can inject that kind of prior knowledge and you will actually, like, especially when you have little data, that will be quite helpful for your predictor. And yeah, so we'll see how it shows up in this supervised learning stuff in a second when we get to the solution. So let's work through expanding this term now. And so we do that in blue like before. So we have log of P, the PDF of the W parameter. Okay, and so here we had, okay, so first of all, okay, I should have added one more assumption here because otherwise things don't really work. Okay, so we had that W0 had like this normal distribution and it was for very large sigma. Yeah. There's going to be one more thing we're going to need that, guess what we do? We just assume it because otherwise the math becomes really ugly, is that if we want to write this guy, which maybe I just write out explicitly to show you exactly where the problem lies if we don't make this assumption. This thing is really the following, right? Okay, and I don't know what to do with this term inside this logarithm without any further assumption. Like, I don't know what this distribution is. I only know the distribution of individual W's. And what I want to do is I really want to use the product rule. Or sorry, not the product rule, the result from probability that when things are independent, I can write the PDF as the product of PDFs. So I really want to write this. So suppose I did write this. When can I write this is the question. Okay, so I really want to write this here. And the reason I want to do it is, first of all, because we had some assumptions on these things, but in particular, like really, it's because this log of this product will simplify really nicely to be a sum, and then I can do things with that sum and so on. Otherwise, optimizing over this will be very, very ugly without the log, because it will be like you'd have to apply the product rule when you take derivatives d times, and it would be very annoying. Okay, but to do this step, what I will need is I will need independence. And I will need independence for all the W's. So that includes W0. So here I have independence for Wj, J1 to D. What I don't have is independence for W0 with respect to every one of these. Okay, so we also assume one more thing, which is that W0 is independent of Wj for all J. But it is not identically distributed. So that's the one difference. It has a different distribution, which is this like essentially having no prior knowledge on it. Okay. So great. Once we get to this step, then we do the standard business with kind of solving these things with the logs and whatnot. Okay. So remove this thing. I'm going to use this product notation to simplify this. As we saw, this like P term, this just means the product from I, and we're going to use J here, J1 to D of P of Wj. Is just to clean up the notation a little bit. Now, I use the log properties, which the log of products is the sum of logs. Okay. So this is the first term in the sum. The second term is going to be here, and it's going to be a sum of logs from j equal 1 to d of these log terms. Okay. Product becomes sum, and then the first term is handled separately. Great. Now, what I'm going to do is I'm going to just plug in the definition of this PDF. And we have that definition because we assume they're normally distributed, these PWJs. Okay, so remove this and plug in this big, long equation for this thing, which looks like 1 over square root 2 pi over lambda. And yes, and here you're going to see that it should have actually, like as we assumed, it should be that the variance is 1 over lambda, not 1 over lambda squared. Okay, and you have this exponential of minus, and then since the mean is 0, what you'll find is it's really, what is it, wj minus 0 squared, but then you don't need this minus 0 in brackets and stuff, so it's just wj squared. And then here you have 2 over lambda. Okay, this is just the definition of the normal PDF, the normal distributions PDF. Then what we're going to do is once again use the log property that log of the product is the sum. And the reason to keep doing this is you notice that here there's no dependence on wj, and here there is. So we want to you basically want to keep separating things that don't depend on the parameter you're optimizing over. And here it's all the way back here. We're trying to minimize this parameter w. It's a vector. And what we want to do is separate the function into a sum of terms, or just basically I just want it to be left with terms that only depend on w. That's kind of why I'm doing all these steps. Notice how this thing has no dependence. Okay, we're going to find that it has no dependence on w because you can treat this as just being a constant prior. And this guy, we're going to separate this term out in a second here. Okay, so back to business. I take this, move it out here, and write this as the sum of logs. Great. And I am almost done at this point. I'm going to do one more step within here, which is remove this log and this exponential thing. And this, right, we've seen this before. And this becomes a minus. Okay. And I'm going to do one more thing to just emphasize the fact that there is 3 terms here. So there's this term, there's a sum over this term, and then there's a sum over this term. Because when we plug it into the optimization problem, we will find that it's nice to see it as these 3 kind of terms you're dealing with. So all I do is I take this sum and add it here as well. So I break it up into 2. What do I have here? I have the log of this guy. No, I don't have the log. Whoops. Okay. I just have this guy. Great. Okay. So we have 3 terms. And this term can even be further simplified. Let's just do that. So notice how in here there's no dependence on j. So it's just the same number. This is just a number summed up d times. So I can remove this sum of d and just plug in d here. It's just d times that thing. Okay, so now I have quite a nice expression. I have a term that does not depend on wj from 1 to d. This is just depends on w0. Then I have a term that doesn't depend on w's at all. And then I have something that depends on wj for j equal 1 to d. Okay, and maybe to make this even prettier, I move this lambda to the numerator. Okay, so now we're starting to get something very interesting. So what are we going to do now? What we're going to do is we're going to plug in this result into here. So let us do that. We go back and we work with this black equation here. We remove this and we plug in our new result. And it does not fit, so we make it smaller. Great. And now what we remember to do is to keep track of that minus that we had out front. So there was a minus here. So we're going to need to make sure that gets applied to all the terms. Minus here, plus here. And we have this optimization problem. Great. Okay, so now let's solve this thing. And to solve it, what we're going to find, first of all, is that this thing is just a constant term that does not depend on w. So we're going to remove this, just like before. Another term that we're going to do the same thing for is the following. Since we've assumed that this guy is normally distributed with a very, very large sigma, you can essentially think of it as having a uniform distribution, which would just mean that its PDF is just a constant. Or you could plug in this PDF and see how the sigma carries through everywhere, and you will find that at the end, if you make sigma very, very, very large, its influence is negligible. It doesn't affect anything at the end. Similar to how we saw here. If sigma is very, very large, you will see you set this to very, very large, this to very, very large. You get 0, you get 0. Okay, so it's not going to have any influence. So I'm just going to remove it right away because otherwise the math is going to be very ugly to deal with. So I'm going to remove this term, saying that we have no prior knowledge on our bias term. We don't really know like this, the bias term of where things start. And this would be like the y-intercept of the linear equation. Okay. So all that, we can take these two guys that are essentially constants, remove them, and we are left with the following problem. Okay. And this gets very curious because we had this for the MLE case, and we saw that, oh, this was, what was this? Okay, so let's look at this guy. We saw that this was almost L hat, but it was multiplied. It didn't have this 1 over n term. Like L hat has a 1 over n. There's no 1 over n here. So if we multiply L hat by n, we get the term above. And we need to just divide by 2 because here there's an extra 2. Okay, so we had this. And now look at this guy. This guy is almost, it's almost the regularization term. So I put in English. In regularized or linear regression, whatever we were doing. It's almost, it's almost regularizer. And in particular, the thing that's missing is that we used to have, okay, let me write this term a little bit more pretty to see why. So notice that this is just a constant, lambda, so we can move it out front. This over 2, we can also move out front. So we get something that looks like this. We really have this. And in the regularized estimate of the loss and whatever, we just had a lambda over n here. So we're just missing an n. Okay, so what that means, okay, what that really means is what we get back is that we are solving for the argument not of L, like n times over 2 of L hat or whatever. If you remember, this thing is actually L hat lambda. It's the regularized estimated loss. In that regularized estimated loss, we had a term like this with a 1 over n, and a term like this with a 1 over n as well. And so what we will find is we need to multiply this by an n over 2 to make up for that 1 over n and to make up for this 2 we have here. Okay. So with that, we are almost done the interesting observation here. Because if you remember from optimization, the argmin of a constant times something is the same thing as the argmin of just the function. Like you can take out the constant and it doesn't affect anything. So you remove that. And okay, so we needed one more. Like, okay. What we should do is we should write that this thing is a function of w, if you remember. So we had this thing before as well. Okay, so now what we have is we have exactly the same thing as we had in regularized linear regression, which is we find, well, we find that like this argmin solution is exactly the regularized least squares, or sorry, the regularized estimated loss predictor thing we had before. Okay, and in particular, this what did we get? We get this thing is that this is W map, and this thing is actually equal to the W hat guy we had before, lambda, whatever it was, something like this. This is like the regularized solution we had before. Okay, so the observation is that this W map thing is the same as the regularized thing, and to make the implication even more like clear of what happens is just remember what we were trying to do to begin with. So, okay. What I mean is, let's begin here again. So we wanted to find f Bayes. And we needed an estimate of this conditional thing, this conditional PDF business. And now we got one. So we got an estimate of this thing. And it's based on W map. It's this guy. This parameter will give us an estimate of this in the way, like in what way? In this way. Is that if we go here, we can remove this. And now talk about this based on W map. Okay. So this is the normally distributed conditional thing, y given x, it's this guy. Yeah, but with not W star plugged in, but with W map. And so what we will find, similar to MLE, is that this equation now looks very, very similar to this. There's an approximation here, of course. And that this is actually the expected value of some new random variable, which is the random variable that has a different mean. Okay, so this thing looks like a conditional expectation of some new random variable y prime conditioned on x, the features. Where now this new random variable, y prime conditioned on x, is distributed with this normal distribution, but now not with W star, which is what we had above, but with W map. Okay. And variance 1. So we got to here, and what does that imply? Well, the expected value, what's the expected value of a random variable if it's normally distributed? It's exactly this. Like for a normally distributed thing, this is its expected value. So we plug that in. So we get that this is just X transpose W map. But this we just saw was the same thing as this like W hat lambda guy, which we talked about for the regularized solution before, which is like the predictor f hat. Okay. So we get that f Bayes, our approximation to it is this f hat, where f hat is this X transpose W map. And this is just the regularized solution that we saw before. Okay. So how did we get this, and what is the interpretation we have? Okay, let me move some of this stuff. So we've got a different way to think about the regularized solution now, and this has like some other intuitions, which is we get this regularized solution when we make some assumptions, which is, as in the MLE case, we have assumed that the conditional distribution of the labels given the features is normally distributed with a mean that has this linear equation. This kind of makes some sense. Like at the end, we end up solving for this estimate of W star, and then we say, oh, our predictor is just the thing that outputs this mean value here. Okay. And now what we did with map is we made an assumption about the distribution of the parameters. Like we had some prior knowledge of what we want or expect the parameters to look like. And what was the observation we had in regularization? Well, in regularization, we said that, okay, if the weights are small, so they don't have a large magnitude, then we should expect a really simple predictor. Like, okay, so that we get a simple predictor. And then if the weights are large, then we'd have a more complex predictor. And notice how this happens here. We make an assumption that the weights have an expected value of 0, which means that they, like, on average, they have an expected value of 0, which means they're very, very small. And it really, how likely that is to happen is dependent on this variance. And so what we'll see is that if lambda is really, really, really small, or sorry, really, really large, then the variance is 0. And if the variance is 0, then we're very, very confident that wj is 0, which means that we think the parameters of the weights are really close to 0 or exactly 0. And that would force, like, this regularization, like, basically that would mean that we would expect the weights and the parameters to be really close to 0. And how, like, when does that happen? That happens when lambda is 0. And that perfectly corresponds to what we saw before with regularization, which is in regularization, we saw that if we make lambda really large, then it forces the weights to be really close to 0. And so, yeah, so the interpretation kind of is the exact same here, but it comes through this fact that what you're doing by making lambda really large, okay, you can see it through this equation here. So before we just kind of took a leap of faith and said, like, let's penalize weights that are really large by adding a term like this. Now we actually got this exact penalization or like way to affect the weights from like a more principled kind of story, which is that, like, if you assume that the weights had some normal distribution and its variance was this 1 over lambda thing, then this is how, like, the resulting story would look like if you tried to solve for an estimate of this. Okay, so this is, I guess, what I wanted to say about regularization, which is you can think of the regularization term lambda as telling you how much prior knowledge you have about the parameters being close to 0. Lambda being very large, you have a lot of reason to believe, or like you really want these parameters to be close to 0. Lambda really, really small, you're okay with the parameters being quite far away from 0. So this kind of allows you to tune how much prior knowledge or how simple you want your final predictor to be, right? Because once again, if the weights are really close to 0, you have a very, very simple predictor, and vice versa. Okay, so that was another really nice way to look at, I guess, this regularization business. And I'm going to answer the question and mention maybe one more thing. So someone asks, is there still a point in this where we need to set the derivative of 0 and solve for the solve to minimize, like the last question? Oh, yes. So we got to here, right? And we need to solve this problem. And we didn't solve the problem here. But like what would you do? You could set this, okay, you would need to take the gradient of this thing. Well, like, okay, you would have to take the derivative for each index and set them all to 0 and then solve this giant thing. And then you'd get this closed form solution, which will be in terms of matrices and so on. And then you would get a closed form solution. And even in the previous chapter about the evaluation stuff, we got to this regularization stuff, but we never solved this in a closed form way, which you can do, but we didn't do it. What we did is we solved for this using gradient descent. So what we said is, like, okay, what's the gradient of this? And then once you know the gradient, then you can find your W's, like your parameters, by just doing gradient updates. And if you do enough of them, you'll get something really, really close to the actual solution of this. But the thing to emphasize, so in practice, you're going to really need to solve this thing. You need to solve this minimization problem. And one way to do it is gradient descent. You also did that in your assignment. You could also do the closed form solution, but here I just wanted to emphasize that the optimization problem is the exact same. So whatever method you use, you're solving the same problem. So yes, but you would really need to solve this. And then to answer some more questions, lambda is derived from prior knowledge now, right? Unlike before, where we chose an arbitrary lambda to control the size of the weights. Yeah, but okay, so like to answer the question is like, it seems you're somehow implying that lambda is derived from prior knowledge, and like I'm saying prior knowledge, but these are all kind of really the same thing, which is like you pick a lambda, and then based on the lambda you pick, you get a different solution, and then it's like you're completely your choice of the lambda you pick. Maybe you have some prior knowledge that the weights should be this, which is like one way of thinking about it, or maybe you just like want the like. Maybe your prior knowledge is that the predictor shouldn't be too complex. Like your data kind of looks like a line. You like visualize it or something. Or like it looks like it could be modeled by a pretty simple function. So you say, okay, lambda should be pretty large because like there's no way the solution should be really complicated. So this is like your prior knowledge. So like, it's kind of the same as just, if you think of the prior knowledge as being like you're setting the variance of the distribution of the parameter in this case, while before you were thinking as you're setting some some value here that kind of penalizes weights. However, it really does become the same story. Okay, and then there's another question, which is how do you get from the almost regularized step to the regularized step? Which is this step to this step, I assume. And I got from there to there simply by just looking at the definition of L hat of lambda. So if I looked at this, well, if I looked at this guy, I would find that its definition is exactly the same as this. Except what it has is it has a 1 over n here. It does not have a 2. And it has a 1 over n here, and it doesn't have the 2. So the question is, how do I get from here to here? Well, what I do is I multiply by n, so that this 1 over n goes away. And I divide by 2. I put a 2 here. And then that's exactly what this term does. So I get that back. And one more question, which is it more likely on an exam to do the more simpler version of this type of question? So yeah, like on an exam, if I ask you to work things out, it will definitely be for like some part of like, even working through this whole solution will probably be a little bit much maybe to ask, but it wouldn't be any more complicated than this, like in terms of a question. And if it is something to do with like something more complicated, like with these steps and stuff, it would only be like some part of it. So you'd be given like for instance, you're trying to solve for whatever WMAP, we've worked out all these steps. Now, you need to work out like simplifying this term and then like what is the correct equation for this after you simplify this and plug it in. So you just need to work out like this part of the steps or something like this. Yeah, which would require you to know like what you have to work out, but it wouldn't require like too much math steps. Would be the intention here. Yeah. So the goal is not on the exam is not going to be for you guys to do like lots and lots of calculations, but it will be to understand what calculations you have to do when. But anyways, more of that will be on Thursday, I guess. And yeah, let's finish with one last kind of observation, which is you can choose a different prior on your parameters. And if you choose a different prior, you get like a different problem to solve. And it turns out there's one other common prior that people like to choose. And it gives you a different kind of regularization, which I haven't talked about yet. But I'm going to just mention it here. So if you assume that the weights, the parameters are Laplace distributed instead of this normally distributed. So notice this is the first time we've seen Laplace in this course, but we talked about it in the probability section. And if you do the same thing, in which you assume they're ID, and that W naught is Laplace, but for a very, very large B, which is exactly the same kind of like variance term. I think it's called like the spread or whatever for Laplace, but same idea. And then you also should assume that it's independent from these as before, but I'm not going to write it. What you will find is then, if you solve for WMAP, which is this like argmax problem, you will get to something like this. And what you have is now this new objective to minimize, like this new function. And what what this thing is it's exactly going to be, okay, it's missing like it's missing this like n over 2 thing as before, but it has a new regularization term. And this regularization does not, okay, it has a lambda like before, but it doesn't have a squared. It has an absolute value. And so it turns out that if instead of squaring the weights, you could have just used the absolute value, and we briefly talked about you could do this for regularization, has the same idea, right? Except you don't square them. This absolute value stuff is called, first of all, lasso or lasso regression. But it comes from, yeah, it comes just a different way of regularizing, but it comes from also using map with a Laplace prior. So yeah, so these are really the two most common kind of regularization stuff that are used. And you can think of them as having different priors on the weights, or just you thinking of, I don't know, somehow coming up with penalizing the weights using absolute value or squared. And yeah, and they turn out to match. And that's all I had to say about this. So that is the end of all this stuff, and basically the end of linear regression for this semester. So what will happen after the midterm is we'll be covering like classification and this thing called logistic regression, which is a way to do classification, still trying to use regression in some way. So we'll see a lot of the same things that we saw here coming up for classification. Okay. Yes, and to maybe answer the last question, which is about just midterm stuff, and I'll make a post, I think, today or tomorrow about this, which is the main focus of the midterm is going to be like chapters 6, 7, and 8, which is everything post midterm 1. But once again, you're probably going to need to know how to deal with some of these probabilities and expectations and stuff. So you'll need to know stuff before, but like you're not going to see like questions where you have to calculate the expected value of something if it's not related to something from chapter 6 to 8. But yeah, more details on Thursday, and I'll make a post about the sections and stuff. And yeah, whatever I got to today will all be potentially on the midterm. Okay, I shall stop recording now. Thank you, everyone.